Now let's look at another example of using Faraday's law. So in this problem, we have a rectangular loop of wire that is pulled into a region of uniform magnetic field. So our black box here is our loop of wire, and we have some pulling force, so someone is grabbing it and pulling it into this blue dotted region where there is a uniform magnetic field pointing into the page. Our goal is to find the induced current and the force on our loop of wire. Now, we are not given any actual values for the magnetic field or the size of the wire or the resistance of the wire. So we're going to leave all of our answers in terms of variables, but that won't stop us from finding the direction of the induced current nor the direction of the force on the wire. And we can still find equations for the induced field and the induced current and the force on the wire. Okay, we will begin as usual by writing down the equation for the magnetic flux. Well, the magnetic field points into the board and is constant, so we can just write it as negative B, where B is the magnitude of our magnetic field, in the negative z hat direction here. Our area here is not the full area of the loop. It is only the area of the loop that fits within the external magnetic field. This region here is the only region of the loop with magnetic flux flowing through it. The region out here has no magnetic field and therefore no magnetic flux. So the area that we are interested in is simply this region here. And again, because our loop is in the plane of the board, we have two options for our area vector direction, either out of the board or into the board. And again, we choose into the board in the negative z hat direction, simply because the magnetic field also points in that direction. Multiplying these two things together, we get our magnetic flux, B times X times Y. Next, we need to take the derivative of our flux with respect to time. Now, naively, we might think, well, B and X and Y, I don't see any T in there. I don't see any explicit time dependence in there. But X is changing. Our loop is moving to the right, and therefore this distance X is changing. So when we take our derivative here, B is constant, my magnetic field isn't changing, Y is constant, the height of the loop isn't changing, but X is changing, and so we get this dx dt term when we take the derivative. Now, of course, we can replace that dx dt with just the velocity, right? The magnitude of dx dt is the magnitude of the velocity of the loop. So how fast am I being pulled into this external magnetic field? So now that we have our change in flux, we can write down the magnitude of our EMF, which is n multiplied by the magnitude of our flux, or our change in flux with respect to time, which is given by here, BYV. So now we know the EMF. We can calculate the induced current by simply dividing the EMF by a resistance. Since we, again, don't have any values here, we just have to leave it as an answer, BY magnitude of V divided by R. All of these are going to be constant. We took the magnitude of the velocity. B is the magnitude of the magnetic field. Y is the height. These are length, so the height is a type of length. Lengths are always positive absolute values. And of course, the resistance is always positive. So everything over here will be a positive value. Now, we know the induced current, the magnitude of the induced current. Let's find the direction of that induced current using Lenz's law. Okay, so what's happening is that we have an external magnetic field into the board, and the flux through the loop is increasing. Not because we are getting a stronger magnetic field, but because as we move to the right, our area is going to increase. So our flux is increasing and the magnetic field points into the board. This tells us that we are going to have an induced magnetic field within the loop, which should oppose that increase in flux and point out of the board. So we're going to have an induced magnetic field pointing out of the board. Okay, well, if my induced magnetic field points out of the board, then my thumb points in the direction of the induced magnetic field, and my fingers curl in the counterclockwise direction, indicating the direction of the induced current flow within the loop. And the current's going to flow all the way around the loop. In order to get a current, you need a closed circuit, so the current's going to flow all the way around the loop, even though only this region over here is actually experiencing the magnetic field and this change in flux. Okay, so the next thing that we need to do is we need to figure out the force on this loop. So before we go through and do some cross products here, let's just think about what regions of the loop could be experiencing a force due to the external magnetic field, and what direction would that force point in? Well, if I take the bottom side of my loop, again, only the region inside of my dotted line experiences the external magnetic field, so I don't need to worry about the parts of the loop that are out here. The bottom part of my loop has a current to the right. It is experiencing a magnetic field into the page, so it feels a force upwards. So I can write the force, the magnetic force on my loop, points upward here. Okay. Next, I can look at this side of the loop. It is inside of the magnetic field. I'll erase this vector here. That was my force of me pulling the vector, or the loop, into the magnetic field. But now we're just worried about the force due to that external magnetic field. Okay, here my current points upwards, my magnetic field points into the board, and therefore I feel a force due to the magnetic field, right, external here, which is to the left. Finally, I can consider this region of my loop here, which has a current flowing to the left with an current flowing to the left, my external magnetic field pointing into the board, giving me a force downward. So on the top of my loop, I feel a force due to the external magnetic field downward. Now, because I have an upward force and a downward force on my loop, these two forces are actually going to cancel each other out. How do I know that they're going to exactly cancel? Well, because of the symmetry of my loop, I know that the current in each of these sections is the same. I know that the length of each of these sections is the same. And I know that the magnetic field that they are experiencing, the external magnetic field, is the same for both of these regions, which means that we have equal and opposite forces, which will cancel out. So the only non-canceling force that will be applied to my loop will be to the left due to the external magnetic field acting on this section of current here. Okay, so taking that cross product, well, I know that the external magnetic field points in the z direction, and my L vector points in the direction of the current, points up. So I can write this as I induced multiplied by my L vector, so I'll just write that as L, has length of y, so it should be y in the y hat direction, crossed with my B external in the negative z hat direction. Doing this cross product, I already know the answer by my right hand rule. And because these two vectors are perpendicular, I know that the magnitude of the cross product is simply the product of these three terms. So this would go like I induced multiplied by y multiplied by the external magnetic field, and it points in the negative x hat direction to the left. And if I wanted to be more explicit, I could substitute in here the values from my induced magnetic field. Doing that quickly, my B, this B here is my external magnetic field as well. So I would get B external squared multiplied by y squared multiplied by the magnitude of the velocity divided by r, and that would all be in the negative x hat direction. So I have two magnetic fields, one from the I induced and one here from my force equation. Y times y, the velocity, and then the r, resistance of my loop, in the denominator, and it points in the negative x hat direction.